Hello, today we're going to be starting the spectrophotometry lab on what is in a brass screw. We're going to eventually figure out the percentage by mass of copper and zinc in a sample of brass. So I recommend using these brass screws. Let's see if I can zoom in. They're little tiny screws like that. They're brass. They're very cheap. I bought a case of 100 of them the first year I did this lab, which was about 8 years ago, and I still haven't used it up. So each group will just need one of these brass screws, and then they should record the mass of the screw before doing anything else. I use my analytical balance for that. So let's go ahead and find the mass. So this one has a mass of 0.9411 grams. If you don't have an analytical balance, that's okay. This lab still runs pretty well, but since we have the equipment, might as well give them the experience using it. Then you're going to transfer the brass screw into just a beaker, and you need to make sure that you have a fume hood for this. If you don't have a fume hood, it's really not a safe lab to be doing. There are plenty of other spectrophotometry labs that you could do. There are also other analysis of mixture labs that you could do because this step really needs the fume hood. You're going to dissolve the screw using concentrated nitric acid. And so what I will do is I'll put a little bit of the concentrated nitric acid in with the screw, put a watch glass over it, and slowly let it dissolve. Then I will vent the poisonous gas that's formed, the nitrogen oxide gas that's formed, and pull that out with the fume hood. Next thing you want to do to start to dilute the solution made from the screw is I put about 50 milliliters of deionized water in another beaker. It doesn't have to be exact. And then I'm going to transfer the solution that was made from the screw into that water. I don't want to add water directly in case there's excess concentrated nitric acid still in the beaker. Remember, the safety mantra is always acid into water. So I'm going to do that first before continuing on with the lab. Then I'm just going to rinse it very lightly with some deionized water from the wash bottle, just to make sure I've got all of the excess copper solution out into this other beaker. And then this solution should sit until ready to be used for the very end of the lab. All right, now we need to create our calibration curve, and in order to do that, we need to prepare dilutions of a stock solution. The stock solution I'm using today is 0.1 molar copper 2 nitrate. This is because we use the nitric acid to dissolve, so there's already nitrate ions in our screw solution, and the copper 2+ ions are the same that we're going to find in the dissolved screw solution, the copper 2+ ions. So we're going to make basically 7 test tubes, but the most concentrated one will just be the stock solution, and the least concentrated will just be deionized water. Do you really need to create those solutions? No, but I like students to have them all lined up in a row so they can really visually see the difference in concentration. All right, so now that you have your dilutions created, it's really nice to have them all lined up so students can see the most concentrated, the least concentration. They can visually see the difference there. Then you want to clean cuvettes and transfer some of the solution to the cuvettes. I have 1 centimeter cuvettes because those fit in the SpectraViz Plus spectrophotometers that I have. Now, recently there have been a number of different apps for smartphones that have come out where you can actually measure the color difference between samples in a single picture. So that is a really cool option if you don't have the technology to be able to do this with a spectrophotometer. You can also do this with a colorimeter, although you might not be able to get it as exact. The spectrophotometer allows you to set the wavelength. We're using 680 nanometers. That's in the orange range because this is a blue solution. It's going to absorb best at the complementary color of light. What we're going to do then is I already put just deionized water in here and calibrated the spectrophotometer so it's reading a 0 absorbance. And you can see it fluctuating a little bit because the spectrophotometer is not covered, so some outside light is getting in. And then we will put each of the solutions we created into a different cuvette and record the absorbance. Now the LabQuest 3 has the option for you to record the data and it will graph it for you in the LabQuest. You can do that, or you can have students record the data by hand. And this is an opportunity for them to learn how to use their graphing calculator to be able to do this. Or they can use a graphing program like Excel, or Vernier has a program, graphical analysis. They can even use Google Sheets. So this is a really cool lab to get them to use technology other than maybe what they're used to. Okay, so I transferred the dissolved screw solution that we added some water to a 100 milliliter volumetric flask. We want to make sure we're using volumetric flask because it's very, very accurate for that one volume. And I just want to dilute it up to the line with deionized water. That way we know exactly the volume of our solution. So when we're doing our spectrophotometry part of the experiment, where we'll get the concentration in molarity, we can then use the molarity and the volume, the 100 milliliters, to convert that into moles of our solution that are present in this solution. All right, so once you've measured all of your dilutions, you should also measure the solution made from the brass screw. And remember, we diluted it so it was total volume of 100 milliliters. You might want to, if it's been sitting for a while, you might want to mix it up a little bit again. And then transfer some of that into a very clean cuvette. About 3/4 filled. And then you're going to record the absorbance of this one just like you did with the dilutions. Okay, so let's get into the calculations for this lab. We used, for our calibration curve, we used a stock solution of 0.10 molar copper 2 nitrate, and we made different dilutions for that. I'm going to show you just one sample calculation. The first test tube that we made was just the stock solution, so it had a 0.1 molar concentration. The second one, we used 8 milliliters of stock with 2 milliliters of deionized water. So the initial molarity was the 0.10 from the stock, and we used 8 milliliters of that. I want to know what is the new molarity when we make the total volume now 10 milliliters. And so when you solve for M2, you get 0.080 molar. And so that's your concentration. You need to do this for all of the different solutions to get your concentration. So here are all of the concentrations for the different dilutions. I calculated the same exact way using that M1V1 equals M2V2. And of course, if there's no stock solution, it's a 0 molar solution. Then I also recorded the absorbance read from the spectrophotometer set to 680 nanometers. So you can see as the concentration decreases, the absorbance also decreases. They are directly related. I also went ahead and recorded the screw, the solution made from the screw, the absorbance of that was 0.493, which falls right in this range. Now, if you were to get an absorbance that was higher than your largest or smaller than your smallest one, it might be worth diluting the screw solution more. So instead of using like a 100 milliliter volumetric flask, you could use like a 250 or 500 milliliter flask. That way, because you want it to fall within the range of values that you found using your dilutions. From here, we are going to graph this. So concentration is going to be our X column and absorbance is going to be our Y. So that way we will get a graph like this with absorbance and concentration, and it will increase in value. This leads us to our relationship, which we come to know as Beer's law. Beer's law is A equals this weird looking E, B, C. It's a Greek letter. But A is absorbance, which is our y-axis. C is our concentration and molarity. And then E and B make up the slope of that graph. So the B is what we call the path length. And because we're using 1 centimeter cuvettes, that means the light from the spectrophotometer has to travel just 1 centimeter through the solution before it reaches the sensor detector at the other side. That leaves this weird E, which is the molar absorptivity constant. And this is going to be unique for different substances and different wavelengths that you're measuring at. So let's go ahead and look at the graph. So I'm using my trusty TI-84 Plus Silver Edition, but you could also do this using a graphing software program instead, or even using the LabQuest itself, or your probeware could have that capability baked in. For the graphing calculator like this, I click on Stat and then Edit, and you'll plug in your values, your concentration in the X column, which is in L1 for me, and your absorbance in the Y column. I have not included the absorbance from the screw solution, just your dilutions to create the calibration curve. Excuse me. Then you need to go to stat plot and make sure that your one of your plots is turned on, and that you have your X list is L1, your Y list is L2, and then you can graph it. Now, if it looks kind of funny, you can hit zoom and then go down to stat, and it will zoom right into the statistics that you have for those L1 and L2 values. And usually you get a really good straight line for this. So you can see those points make a very direct correlation. Now we can find the equation of that line using a linear regression. And to do that, you'll hit stat again, and then calc, and go down to linear regression. For this calculator, you need to tell it first the X. So X we have in our L1, list 1, and then comma, L2 is for our Y, and then hit enter. Some calculators it will like prompt you, like which one is for X and which one is for Y. So it just depends on what you're using. And then hit enter, and then it gives us our line of best fit for those statistics. And so we had a slope of about 5.199, and then a y-intercept of negative 0.0118. In a perfect situation, your y-intercept would be 0, because 0 concentration should have a 0 absorbance. But because of fluctuations in the graph, your line of best fit probably won't go exactly through the origin. Okay, so now we can use the equation for that line of best fit. where y is the absorbance, x is the concentration. Remember, the slope is the path length, which is 1, times the molar absorptivity constant, which is 5.12 in this case. And this tells us about the errors involved, but I'm going to go ahead and plug in for y the absorbance that we measured for that screw solution, the 100 milliliter solution we made when we dissolved the brass screw. Now this is going to work because the brass sample is composed of both copper and zinc. When it reacts with the nitric acid, it dissolves them into ions. The zinc ions are colorless, so they do not affect the absorbance at all, but the copper ions will affect the absorbance at 680 nanometers because they are blue color. So when I plug in the absorbance from the screw, I can solve for x, which is the concentration, and that winds up being the concentration of the copper ions, because that's what's being picked up by the spectrophotometer. Now that I have the molarity, I can multiply that by that total volume we made from the screw solution, which was 100 milliliters or 0.1 liters. Molarity times liters gives us moles. So this is how many moles of copper were in that 100 milliliter volumetric flask. From there, I can convert moles to grams using the molar mass of copper. And we found that there was then 0.627 grams of copper present in that volumetric flask, which means that there must have been that many grams of copper in the screw. Now, if you go way back to the beginning, the original mass of the screw was 0.9411 grams. So if you divide and multiply by 100, you'll get the percent by mass that was copper. And so when you multiply there, you get 66.5% of the screw was copper by mass. That means if you subtract from 100, the other 33.5% of the brass screw must have been zinc. We just had to calculate that indirectly because it was colorless and would not be picked up from the spectrophotometer. Now let's talk about some sources of error. A really common one that they talk about is fingerprints or smudges on the cuvettes. If you had a smudge on the cuvette, that would increase the measured absorbance because it's blocking light from passing through the cuvette. So that would mean your absorbance was higher than it should have been. If your absorbance was higher, then your concentration would have been higher, your moles would have been higher, your mass would have been higher, and then your percent of copper would have been higher. Another source of error, sometimes we'll talk about if there was leftover water from cleaning the cuvette. If there was extra water in the cuvette, that would lower your measured absorbance, which would lower your calculated molarity, lower your calculated moles and grams, and therefore lower your percent by mass of copper.